So we've deciphered the solstices. Next, let's check out the equinox. We know that the subsolar point migrates from 23.5 degrees north on the June solstice to 23.5 degrees south on the December solstice. At some point in between, it must be at the equator. Those times, there are two during the year, one in the spring and one in the fall, are called the March and the September equinox. So, at the equinox, the vertical rays hit at the equator. Consider that. Equinox and equator, they both have the same root. So this is how you can remember that at the equinox, the vertical rays hit at the equator. We can now find the edge of the circle of illumination by going up 90 degrees from the subsolar point and down 90 degrees from the subsolar point. For the equinox, the calculation is easy. 0 plus 90 puts you at the North Pole, and 0 plus 90 to the south puts you at the South Pole. So the edge of the circle of illumination on the equinox are at the two poles. Everywhere on this side is within the light, and everywhere on this side is in darkness. Importantly, notice that 50% of the equator, half of the equator, is within the circle of illumination. Thus, day lengths are 12 hours long, 12 hours a day and 12 hours a night. As you move north or south, look at this. The percentage of each parallel remains at 50%. So that means on the equinox, everywhere on Earth basically has 12 hours of sunlight and 12 hours of darkness. Indeed, equinox is Latin for equal nights. 12-hour days and 12-hour nights. So that's pretty cool. Everywhere on Earth on the equinox has a 12-hour day and a 12-hour night. You might remember for the solstices, the equator also had 12-hour days and 12-hour nights. Indeed, the equator actually has 12-hour days and 12-hour nights all throughout the year. The circle of illumination always bisects the equator, always cuts it in half. So you can imagine living on the equator, you always have 12-hour days. Sun always rises around 6 a.m. and sets around 6 p.m. Well, depending on where you are in your time zone. The time may vary slightly. But it doesn't matter if it's the middle of the summer or the middle of the winter, you'd have the same day length. This is why places near the equator don't bother with daylight savings time. Study this figure of the equinox and practice figuring out where the subsolar point is in the circle of illumination and looking at day length. And then draw some diagrams on your own. Your diagrams don't have to be really detailed. They can be fairly simple like mine here, although maybe you can do a better job of making your Earth look like a circle. Anyway, I've drawn the Earth and the Sun. I've drawn some direct rays coming in, hitting the Earth at 90 degrees, and I've drawn tangent rays that just barely skim the edge of the Earth. On the equinox, we know that those direct rays actually come in, right at the equator, 0 degrees. The tangent rays then, 90 degrees up, that's the North Pole, and 90 degrees south. All right, and everywhere over here would be in the dark as the Earth rotated on its axis. And every parallel is roughly bisected by that circle of illumination, so you get 12-hour days and 12-hour nights. Again, pause the video and draw this simple diagram. I also encourage you to draw the other important parallels just for practice, the Tropic of Cancer, the Arctic Circle, the Tropic of Capricorn, and the Antarctic Circle. You only need one drawing for both equinox because the drawings are identical. Check out this diagram. Approximately what month of the year do you think this diagram represents? There are two possible answers, and you can figure it out. You know that on June 21st, the direct rays hit at the Tropic of Cancer, 23.5 degrees north, and on roughly December 20th, the direct rays hit at the Tropic of Capricorn on the winter solstice. And in between there, on the two equinoxes, the direct rays hit at 0. So we might have June, July, August, September, October, November, December, January, February, March, April, May, June. So with that in mind, you can estimate 2 approximate times of the year where the subsolar point, the direct rays of the sun, would hit at 10 degrees south. One last point just to review. Everywhere within the tropics here has 2 days of the year where they're going to get the direct rays of the sun. So that's the most intense radiation. And outside of the tropics, we never get the direct rays of the sun. So let's look at a map that shows the average annual radiation, the average annual insolation, incoming solar radiation. You can see red, orange, and yellow are more intense, and areas within the tropics, of course, get more intense radiation throughout the year because they get more direct rays of the sun. If you remember several video clips ago, we talked about when the Earth's sun came in at a lower angle, there was more atmosphere to reflect and absorb and refract the sun's radiation. Additionally, when a sun's radiation comes in at a lower angle, it's spread over a larger area and is less intense. So all we've pretty much done so far is to really explain for ourselves why these regions in the tropics are warm. They get a lot of direct radiation and almost direct radiation throughout the year. Okay, we now have a really solid understanding on how the seasons work and the Earth-Sun relationships on the 4 special days, the equinoxes and the solstices.